Assalamualaikum and hi everyone. We meet again. Today we will continue our lesson still under topic rate law part 3. So what we are going to learn today, we want to determine the order of the reaction involving a single rate turn using first initial rate method. Alright, second the unit of rate constant K. And then number 3, half-life based on the graph of concentration against time. Okay, number 4, linear graph method based on the integrated rate equation and also rate law. Alright, so there are 4 methods that we can determine the order of duration. So the first method is by using initial rate method. Okay, second, the unit of rate constant K. Number 3, half-life method based on the graph of concentration versus time. Number 4, linear graph method based on integrated rate equation and also rate law. Right, so we take example method 1, that is referred to the initial rate method. Given in the table here is the initial rate turn concentration for oxygen gas and nitrogen monoxide gas. And also given in the table here is the initial rate. Okay, so how that we can use the initial rate method to find out the order of the reaction? Okay, so first of all, you have to write the rate law. So rate is equals to K concentration O2 power of M and times concentration NO power of N, where M here is the order of the reaction with respect to oxygen gas and N here is the order of the reaction with respect to NO. Right, so next we have to compare two experiments in which the concentration of one reactant varies and the concentration of the other reactant remain constant. So it's up to you whether you want to start with the concentration of O2 or you want to find out the concentration of NO. Right, let's say I want to find out the concentration of oxygen gas. So therefore, I have to find out the concentration of NO which remain constant. So based on the table, concentration of NO that is remain constant is referring to the experiment 1 and experiment 2. So we just compare and we can cancel out since it is constant and have the same power. So we can cancel out. So therefore, we can compare the concentration of O2 for experiment 2 with concentration of O2 of experiment 1. Since the power of here is the same, that is power of M, so therefore we can factorize and become like this. Alright, so next step, you can substitute the rate, value of rate, initial rate for experiment 2 and also experiment 1. For easier calculation, alright, so you can place the rate that is bigger value divide by the initial rate that is a smaller value. Okay, alright. So next, substitute the concentration of O2 experiment 2 divide by concentration O2 experiment 1 power of M. Alright, so therefore from here, okay, you will get 2 is equal to 2 power of M, where M is equals to 1. Okay, therefore we conclude that the reaction is first order with respect to oxygen gas. Right, so next we want to find out what is the value of N. We can use the same method, so we can compare experiment 3 and 1, okay, in which the concentration of O2 is held constant, meaning that same value. And the concentration NO is doubled, okay, so meaning that varies, okay. Right, so rate 3 divided by rate 1, okay, and then we can cancel out the concentration of O2 since it is constant, right? So, and then we can cancel out the K. K is also constant, and therefore we will get like this. Since both concentration of NO have the same power of. So therefore we can factorize and become like this. Okay, next step, you can substitute. Okay, so same as previous. It is for easier for your calculation, you have to place the rate, initial rate that is greater number divide by the smaller number of initial rate. Okay, so we can cancel out the unit. Okay, this one unit can cancel out, and therefore we will get 4 is equals to 2 power of n. So, and then n here is referred to 2. Then write the conclusion. Okay, order of the reaction is a second order with respect to NO. So, from here we can write the rate law. So, rate is equals to K concentration O2 times concentration NO power of 2. So, next for the second method that we can use the unit of the rate constant to identify the order of the reaction. So, for example, like in this question, hydrogen iodide decomposes to hydrogen and iodine at 443 degree of Celsius according to the following equation. So, we have this equation. So, the rate constant for the decomposition at 443 degree of Celsius is 30 dm cube per mole per minute. How long does it take for the initial concentration of the Hi of 0.1 to reduce to 0.01 molar at this temperature? So we have the initial concentration and the concentration at the given time. So how long here? Meaning that we want to calculate the time taken for the concentration of Hi become 0.01 molar. Okay, and then B, how fast does the reaction occur if the initial concentration of Hi is 0.75 molar? So, how fast here is referred to the rate. Now, whether the rate of reaction is fast or slow. Okay, and then this is the initial concentration of Hi. Right, so based on the unit of K, right, so that is 30 dm cube per mole per minute. Or dm cube per mole here is per molar per minute. So this shows that the order of the reaction is the second order. So that's why the first A here, how long, we want to calculate the time, and then given to you the initial and also the concentration at T. Okay, so the first A here, you have to use the integrated rate equation, right? For the second order. Okay, so because of the second order, you have to choose this formula, this integrated rate equation. And then substitute A here is referred to the concentration, Hi. Okay, alright. So next substitute. Okay, we substitute Hi at T. Okay, 0.01 and initial concentration of Hi 0.1. Okay, so 30 is referred to the K and we want to find out T. So therefore we calculate T is equal to 3 minutes. For part B, how fast, meaning that we want to calculate the rate law. Okay, right. So first of all, because the second order, so we have to write the rate law. So remember, rate law is only referred to the concentration of the reactant only. So rate is equal to K concentration Hi power of 2. Okay, and that is already given the initial concentration of Hi is 0.75 molar. Substitute. Okay, we want to find out the rate here. Substitute into the concentration of Hi and also the value of K. And then we get the rate of reaction is 17 molar per minute. Right, so method number 3, half-life method based on the graph of concentration versus time. So this is the example of question. The following result were obtained from an experimental investigation on dissociation of dinitrogen pentoxide at 45 degrees of Celsius. So this is the equation. The given here is the time and also the concentration. Alright. Alright, so plot graph of concentration N2O5 versus time. So meaning that the value of concentration N2O5 is the y-axis and time is referred to the x-axis. And then from the graph, we have to determine the order of the reaction and the rate constant. Alright. So therefore, remember, notice here, this is time 10 power of negative 4 molar. Okay, right. So this is example of the graph. So make sure you have to label the y-axis and also the unit, molar. Okay, x-axis time, and in the table, data in the table given, the unit of time is minute. And then when you plot the graph, you will get a curved graph like this, right? Okay, we start with the initial concentration here. Okay, refer back to the table. So initial concentration here is 176. So when we count half of it, so it's somewhere here. Okay, we have to find out the first half-life. Okay, and then you have to read the time here at the x-axis. It's 20 minutes for the first half-life. And then we have to compare half of this point. So somewhere here, right? So we get the second half-life. And then how to read the time. So you have to refer to the x-axis. Okay, so somewhere here, right? So therefore, it becomes 40. So the differences here, okay, the first half-life is 20 minutes. And the second half-life also 20 minutes. So it shows the differences is constant. How to explain? This is simple answer. Okay, based on the above graph, the time taken for the concentration of N2O5 to change from 176 times 10 power negative 4 molar to 88 times 10 power negative 4 molar is 20 minutes. Okay, so this is referred to the first half-life. Okay, time taken for the concentration of N2O5 to change from 88 times 10 power negative 4 molar to 44 times 10 power negative 4 molar is also 20 minutes. This is second half-life. Right, so what conclusion here? The half-life for reaction is a constant. Okay, same, 20, 20. And does not depend on the initial concentration of N2O5. So we can conclude that the above reaction is the first order reaction. Okay, and then refer back in the question as to determine the order. So this is first order reaction. And then second, determine the rate constant. Right, so the rate constant, you can use the formula of T half for the first order. Okay, so we know that T half is equals to ln 2 over K, right? So we want to find the K. The first half-life is 20 minutes. And then ln 2 over 20. So we'll get K is equals to 0.03 per minute. Okay. Alright, next, method number 4, linear graph method based on the integrated rate equation and rate law. Alright, so it's given here is the time in minute, okay, concentration of C4H6 in molar, okay, and then 1 over concentration C4H6 per molar. Okay, so the data in the table above were obtained from the dimerization of 1,3-butadiene, that is referred to C4H6, okay, at 600 K. Use the data above to plot a graph 1 over concentration C4H6 against time. So meaning that this is referred to the y-axis. Okay, this data is y-axis and this data is the x-axis. Okay, and then based on the graph, determine reaction order, whether 0, first or second order, and then you have to explain. Okay, and then you have to determine the value of rate constant K based on the graph. When you plot, suppose you get like this, right? So don't forget to label the y-axis 1 over concentration C4H6 and also the unit per molar. Okay, and then x-axis is time and also the unit minutes. And then when you plot, you will get a straight line graph here, right? With the initial here is 60. Okay, refer back to the table. Alright, so somewhere here is with the initial 1 over initial concentration of C4H6 is 59.2. Okay, alright, so here this is referred to 1 over concentration C4H6 not. Okay, this is not. Okay, and then this is positive graph. So therefore, this is y equals to mx plus C. Okay, where C here is the 1 over concentration C4H6 naught. Okay, and then Y is referred to 1 over concentration C4H6. Okay, and M here is referred to K. Okay, and then X is referred to T. So actually we will get this formula, this integrated rate equation. Right. So this is how you can explain. So this is second order. Okay, because it produces straight line, and this is agreed with this integrated rate equation for the second order. Alright, so next, how to find out the value of K. So the value of K here is referred to the slope of the graph. Okay, so you have to find out the gradient. What is the gradient? Or the slope of the graph. Okay, you can take any point here. So this is some example of the calculation. So this is y2 minus y1. This is x2 minus x1. Alright, next you can get K is equal to 0.873 per molar per minute. Alright, so this is the summary for zero order. You have to know first order and the second order. Okay, we have finished topic 1.1. So until we meet again in the next lesson. Okay, Assalamualaikum and bye.